Uh, Calc 1. All right, before we talk about quantum theory, we have to talk about light. And we're going to kind of keep going till we get to the atom and how I came up with the theory of atoms. When we talk about light, generally we're talking about visible light. It's only a small part of what we call the electromagnetic spectrum, a very tiny part that we can see. So, the wavelength nature of light, if we look at a wave, its symbol is lambda, that little Greek letter there. That's the distance between identical points on successive waves. So if you look from the peak to the peak, that is one wavelength. Or from the trough to the trough. Now, you see the mean line drawn through the wavelength. From the mean to the top of the peak, that's the amplitude. So that'll tell you pretty much how intense it is, or how, if you're talking about sound, how loud it is. Frequency, and its symbol is nu, is the number of waves that pass through a particular point in 1 second. So I come up to you and I do this on the top of your head. Maybe a little annoying, but if I increase the frequency, I start doing this at the top of your head. Which one has more energy? The second one. Okay? So the frequency is the number of waves that pass through a particular point in 1 second. And amplitude, like I said, is the vertical distance from the midline of a wave to the top of the peak or the bottom of the trough. So if you have a radio station on and you have, let's say, 94.7 country, shoot, I'll listen to country. Turn the volume up, you're turning the amplitude up. If you change the wavelength, you change the station. The speed of light, I'm sure you're through a vacuum, everybody knows this, 2.99792445 times 10 to the 8 meters per second. We're going to use 3. The speed, wavelength, and frequency are related by the equation. Speed is equal to lambda times mu. So you see, as the wavelength gets larger, the frequency has to get smaller. It always has to equal 3 times 10 to the 8. So as the frequency gets smaller, the energy here's a high frequency. Here's a low frequency. Which one has more energy? The high frequency. So as the frequency goes down, the energy goes down. So wavelength, in this case, is expressed in meters. Frequency is per second. So here we're talking about a laser, a neodymium YAG laser, The wavelength is 532 nanometers, which is in the green area. So this is a green laser. What's the frequency of the radiation? And that equation, frequency, we use C equals lambda nu. Nu is equal, that should say C divided by lambda. For some reason, when it translated it in the smartboard, it's a question marks there because it didn't know what it was supposed to be. So C is 3.0 times 10 to the 8 meters. I gave you the wavelength in nanometers. To make this work, you have to change it to meters. There's 1 times 10 to the 9 meters, nanometers in a meter. So we're going to multiply the 532 by 1 times 10 to the minus 9. Essentially divide by 1 times 10 to the 9. Find out we have 5.32 times 10 to the minus 7 meters. So the answer to that is the frequency is 5.64 times 10 to the 14th per second. So that wavelength is going by pretty fast. So it's pretty high energy. And you think if you're treating skin lesions of that, you pretty want to get rid of it. Are we okay with that? So here's the electromagnetic spectrum, and you see that little point in the middle. That comes out here. That is our visible light. And we all know the colors of the rainbow, right? Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. So we start red, 700 nanometers, down to violet, 400 nanometers. Okay, everybody's observant. Sometime other in your life, you've seen a rainbow. What's the top color in a rainbow? Yeah, you looked at rainbows your whole life, you don't know the top color. No. Red. Red. What's the bottom color? Violet. So if I just look at this, which one has the shorter wavelength? Violet. So if it has the shorter wavelength, what's its frequency going to be? Higher. So what's its energy going to be? Higher. So violet is higher energy than red. So if we come down here, so the 400 nanometers, right? Lower wavelength, higher frequency, higher energy. If we go just below that, where we can't see, we're the ultraviolet, UV. Sun lamps, tanning lamps. Where else do we find UV lights? Slack lights.
Oh, yeah.
Those aren't UV lights.
Past the ceiling sun.
Oh, yeah.
On the next floor?
Yeah.
No. Well, yeah, sunlight gives you UVA, UVB, because we have the whole electromagnetic spectrum. Where else do you see black lights? See them in restaurants? See them in hospitals? Because they kill germs. So,
We also have them in cabinets upstairs for the goggles.
yes, for the cabinets upstairs. That's why I turn them on, because that kills any of the little buggers that come off of you onto the safety glasses, so they can get onto the next people. Okay, so that's UV. I have one in my furnace to kill mold and all that other crap. So now we go down even higher energy. We have X-rays. So you get an X-ray. What do you see? Bones, because the X-rays don't penetrate the bones. Then you get even higher energy. You're down in the gamma rays. Gamma rays go through everything except lead and the thickness of lead. So people who are treated for cancer, radiation therapy, cobalt-60, gamma rays go right through your skull. X-rays, obviously don't. You can see your skull. Gamma rays are everywhere. If I brought a Geiger counter down here right now and turned it on, you'd hear click, 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 because they're coming right through the ceiling. You can't, don't do this, you can't avoid them. Okay? Cosmic, you call them cosmic rays. Other end of the spectrum. We're at red. Above red, we're at infrared. So you see those are the heat lamps that, Wendy's and McDonald's and fast food places that keep food warm for days. Certain nighttime goggles, you see infrared, so you can see the heat signatures. Lower energy, you get the microwave. Okay. Lower energy, now you're in your cell phones. Lower energy, you're in your FM radios. Then the lower energy, longer wavelength, you're in your AM radios. Which explains why AM reception is lousier than FM. Not as much energy. It gets a little cloudy, and then all of a sudden your AM goes. You can still hear FM pretty good. So, an electromagnetic wave has an electrical field and a magnetic field. And they travel perpendicular to each other. That physics, you've probably seen this. So you can take a nail, wrap a wire around it, connect two ends to a battery, and you can make an electromagnet. So you have an electric field, and then you have a magnetic field that's perpendicular. In physics, so you have the right-hand rule and the left-hand rule. Same wavelength, same frequency, but they're in mutually perpendicular planes. So if someone did this double slit experiment, they had light shining onto a screen with a slit. When it goes through the slit, it propagates a wave. Think of like a ripple in a puddle. Then you get a second screen, and you have two slits. And there's two slits down, go through there, you propagate waves. And you can see after that, the waves are crossing each other. And when you hit the detection screen, you see light areas and dark areas. So if I look at a wavelength, or sinusoidal curve, you can have that. The second one, if it meets, be like that, or it can be just the opposite. When they meet and they match up, it's called being in phase. And they add to each other, so it becomes brighter. The amps add to each other. When they meet opposite each other, where the high and the lows are the same, that's called out of phase. And the amplitudes subtract from each other. So you see no light. So you see when these light, after the second slit, where they interfere with each other, you get what's called an interference pattern. So you can see bright lights where they're in phase, where you don't see any light. Dark spot, it's out of phase. And then when it's slightly out of phase, you see it's bright, it kind of gets dimmer, until it's completely black, and then starts getting brighter again. So you can have slightly out of phase.
So the energies just cancel each other out?
Yes, they're out of phase.
What happens when you have like two different colors out of phase, two different frequencies out of phase?
Then you get into something called birefringence. I don't think you want to talk about that. Quantization of energy and photons in the Okay, if you heat a solid body, it emits electromagnetic radiation known as black body radiation over a wide range of wavelengths. You can see that. A prime example of that is a toaster. You heat that wire, you see radiation. You feel heat, you see light. So you have a bunch of wavelengths here. You see it turns, little coils turn red, so you see whatever 700 nanometers plus or minus, red, orange, and you feel any heat. trying to explain black body radiation using the wave theory is close, but not really. So this man Planck, he developed a model proposing that radiant energy can only be emitted or absorbed in discrete quantities, like small packages or bundles. He called a small package quantum, the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. So that was defined as the energy is equal to h nu, where nu is the frequency. H is Planck's constant, which everybody knows is 6.63 times 10 to the minus 34 joules a second. And I hope you realize by now when I say what everybody knows, I mean nobody knows it, but nobody remembers it. So how much more energy per photon is there in green light of a wavelength 532 than in a red light 635? So we're going to use erase Planck's constant E equals h nu. Well, we know Planck's constant, but it's a constant. Nu is what? Frequency. Did I give you the frequency? No. What did I give you? Wavelength. Damn. Can I get the frequency from the wavelength? Yeah. C is equal to lambda mu. Frequency is equal to C divided by lambda. We just did that. So here we changed the two, and again it has to be in meters, so we changed the two wavelengths to meters. And there's Planck's constant, and we substitute those in. For the first one, the green light hits 5.64 times 10 to the 14th per second. Plugging it into the energy, turns out to be, we have 3.74 times 10 to the minus 19 joules. If we do the same thing for the second wavelength, the 630, the red, is 3.13 times 10 to the minus 19 joules. So you can see the green has more energy than the red. It's a larger number. And that's what we said conceptually. We said violet, in a rainbow, violet was higher energy than red. You know, green is somewhere in between, so green is still higher than red. So if you take the difference between the two, the green light has 6.1 times 10 to the minus 20th joules more energy. Doesn't sound like a lot. Small number. But we're talking about small, we're talking about photons. Okay. What happens in the photoelectric effect? Electrons are ejected from the surface of a metal exposed to light of at least a certain minimum frequency called the threshold frequency. Again, we can't explain that by the wave theory of light. So here we have a vacuum tube with plus and minus a piece of metal, voltage source, and meter, and we're going to hit it with incident light. Now remember I said the energy comes from where? The frequency or the wavelength? Frequency. So if I have a certain wavelength of light, does it matter how intense it is if it doesn't have enough energy? So here's my electrons in the metal. So here's my electron. So I have, here comes my wavelength. Did I knock it off? If I change the intensity, I'm still hitting it with the same energy. Now if I change the frequency, oh, that was good.
Yeah,
I can do that.
Easier to flex.
I can knock it off. But there's a certain minimum amount. I mean, this is held with a certain amount of force, right? So if I just hit it with enough force, knock it off, that's the minimum. All right. If I hit it with a lot more force, I still knocked it off, right? But what happened to the particle? What do we call that kind of energy? Kinetic. So the energy that I needed to knock, this was held by what's called binding energy. The electron was bound to this metal. So I had to hit it with enough energy to overcome the binding energy. If I hit it with more energy, not only did I overcome the binding energy, but I added kinetic energy. Make sense? So this man, you may have heard of him, Einstein, he assumed that a beam of light is actually a stream of particles. He called those particle lights photons. Then he used Planck's equation. So now we have the energy of the photon is equal to h nu. So same equation. So if the frequency of the photons is such that, and it should be h nu, not h question mark, h nu, is exactly equal to the energy that binds the electrons in the metal, then the light will have just enough energy to knock the electrons off. If you use higher frequency, not only will you knock it off, but you're going to add some kinetic energy to it. Make me bend over. I'm old. Jeez. Okay. So you have the kinetic energy and the binding energy. So calculate the energy joules of a photon with a wavelength of 5 times 10 to the 4th nanometers. So that's in the infrared region. And one with 52 nanometers, the ultraviolet. Calculate the kinetic energy of an electron ejected by a photon in B from a metal with a binding energy of 3.7 electron volts. Now we're introducing something else. So again, like we did before, we're changing the wavelengths from nanometers to meters. And it turns out electron volts can be changed to joules. It's 1.602 times 10 to the minus 19th joules per electron volt. So we know the binding energy in joules is 5.9 times 10 to the minus 19th joules. So we're going to use that for part C. I'm sorry, go back one slide. Okay. Oh. So again, solving for the frequency, that's for the infrared. The energy is 6.39 times 10 to the minus 21 joules. If we do the same procedure for the ultraviolet, we have 3.8 times 10 to the minus 18 joules. That's a lot higher energy. That's essentially 1,000 times more energy. 10 to the minus 18th versus 10 to the minus 21st. So before we set energy, is equal to kinetic energy plus W, so H nu is equal to K E plus W. Rearranging it, K E is equal to H nu minus W. So we put in H nu, this is for the second one, minus the binding energy we calculated a couple slides ago. The kinetic energy is the difference, 3.2 times 10 to the minus 18. You see, most of the energy from the ultraviolet light was transformed to kinetic energy. Not only do we have enough to knock the electron loose, but we added a lot of energy to it. To the photon. Are you okay with that? Yes, no, maybe. Oh, you're going to be on the little thingamajigger. All right, next time we're going to go into Bohr's theory of hydrogen atoms. Bohr's theory. You guys have lousy kinetic energy.
I'm gonna use thunder and throw.
Great.
Because I want, okay. I didn't want to tag him.
I'm sure there's a lot of people right now that like to throw it real hard, see if you can stick it. Okay.
I got pushed out this morning. I have too much sympathy for you.
All right. Have a good weekend. See you Tuesday. Maybe we'll have some fun Tuesday in the lab. Again, check your test. Make sure you take that makeup test or upgrade test or whatever we're calling it.
And it can only help us, right? These drugs.
If you don't take it, I add no points. I mean, it just goes into a column in Blackboard. It gets added to your total.
Yeah.
So if you don't take it, you get 0. It doesn't. At the end, whatever you do, do not try to do percentages. Because you're going to come out with over 1,000 points. I just look at based on 1,000 points. So I just look at your total in the end. If I give you 1,100 points and you got 700, it's a C. 700, 800's a B, 900's an A. But if you look at the percentage, you'll do 700 out of 1,100 and say, oh, I only got a 68. No, I got 700 out of 1,000. Enjoy your week. Stay out of toxic clouds.
Will you just
I got it. I'll see. I already got it anyways. Okay. No. You only sent me the one. If I get this thing come back up here.
I got my test up already.
Oh, you do?
And I started writing down which ones I got wrong.
All right, you should be able to see the answers.
Yeah.
Okay.
But
So you got it up?
Yeah, I do. I
Okay.
just don't understand where I did wrong. The only one that